Imagine being in a city in broad daylight. You were probably walking around to admire the tall buildings when suddenly a plane just flew across the blue sky. Have you ever wondered how fast it goes as the distance between you and the plane increases? Did you know that during the recording of a rocket launch, the camera angle stays focused on the rocket by having the necessary rate of change? Let's discover more about the relationships between rates and quantities in this lesson. What exactly are related rates? Related rates involve either increasing or decreasing rates of change. Going back, a rate of change is a rate that describes how one quantity changes in relation to another quantity. In related rates, it always involves two or more quantities that change with time. And yes, the plane that you just saw earlier is one of the many real-life scenarios wherein related rates are applied. Now that you are familiar with its definition, let's try to solve for them. We can solve problems involving related rates in 5 steps. Visualize the problem. It would be best if you can draw a diagram. Write the given data. Analyze the problem and figure out which are known and what is asked. Construct your equations. Relate your equations to the variables concerned. Differentiate both sides with respect to time. Use the chain rule and implicit differentiation. Substitute your values to solve for the required rate of change. With the said steps, we can solve for problems involving related rates. Let's try. In this modern house, a person left a 15-meter ladder leaning on the wall. Let's take a closer look. The bottom of the ladder is sliding away from the wall at the rate of 1.7 meters per second. How fast is the top of the ladder sliding down when it is 5 meters above the ground? We can visualize this problem this way. Let's write down our known and unknown data. Y equals 5, z equals 15, and dx over dt equals 1.7. We are looking for dy over dt. We will be using our knowledge in trigonometry to solve. Using the Pythagorean theorem, x squared plus y squared equals z squared. Let's input our y and z values. Simplifying, our x will be 14.14. We will now differentiate both sides of the equation. Substitute our values and isolate the dy over dt term, which will leave us with the answer, negative 4.8076 meter per second. Notice that it is negative because the ladder is moving down to the ground. Let's try this one. A paper cup in the shape of a right circular cone has a height of 15 centimeters and a radius of 5 centimeters. The bottom of the cup is punctured so that the water leaks out at the rate of 4 pi over 3 cubic centimeters per second. What is the rate of change of the water level in centimeters per second when the water level is 10 centimeters? Let's organize our given data. H equals 15, r equals 5, and dv over dt equals 4 pi over 3. We need to find dh over dt when h equals 10. We will first write our radius in terms of height. We have a radius of 5 and a height of 15, which means that r is equal to 5h over 15. Using the volume formula for cones, 1/3 times pi times r squared times h, we will plug in our radius. Simplifying, we will have a result of v equals 25 over 675 h cubed pi. Next, differentiate this equation on both sides, which will give us dv over dt equals 1 over 9 h squared pi dh over dt. Input our known values, dv over dt, which is 4 pi over 3, and the height, 10. Let us simplify this equation. Isolating the dh over dt value, we will get 9 over 25 or 0.36 centimeter per second. For the third and last problem, The recording of a rocket launch at the National Space Center will happen. What rate of change is necessary for the elevation angle of the camera if it is placed on the ground at a distance of 4,000 feet from the launch pad, and the velocity of the rocket is 500 feet per second when the rocket is 2,000 feet off the ground? Let us list down all our given values. H will denote the height, while theta will be the camera angle. H equals 2,000, dy over dt equals 500, and x equals 4,000. We need to get d theta over dt when h equals 2,000. To do so, we will use an equation relating h and theta. We know that this problem resembles a right triangle, thus, trigonometric functions can be used. Recall that tan theta is the ratio of the length of the opposite side to the length of the adjacent side of the triangle. Thus, we have tan theta equals h over 4,000. This will give us an equation, h equals 4,000 tan theta. Let us differentiate this equation with respect to time. We will have dh over dt equals 4,000 secant squared theta, d theta over dt. We need to find values for this equation. Knowing that we already have the value for dh over dt, we will only find secant squared theta. Recall that secant is equal to hypotenuse over adjacent. Let us determine the measure of the hypotenuse by using the Pythagorean theorem. 4,000 squared plus 2,000 squared equals z squared. Simplifying, we now have z equals 4,472.14. Plugging these values in the equation, secant squared theta will be 1.25. Substitute the values in our equation, then simplify. Isolating the d theta over dt term, we will have 1 over 10 or 0.1 rad per second. Today we learned about related rates, the steps to solve them, and its whole solving process. Thank you for watching this video, and we hope that you learned something new. This is a performance task in basic calculus created by SSOT Group 3. Antiquera Jennica, Balanlay Miles, Dimasukal Jordan Michael, Recto Allan, Dumlao Margarette, and Policarpio Atasha. Editing, animation, and voice by Jennica Antiquera. Vector arts and illustrations by Freepik. Music by freestockmusic.com. Problems involving related rates were grabbed from Jesus P. Mercado's Next Century Mathematics Basic Calculus and from math.libretexts.org.